Hi everyone, today we are going to talk about experimental design and sample size calculation. My name is Hao Zeng, a master level biostatistician supervised by Dr. Ma-Yin Kong, and we are from Biostatistics and Bioinformatics Core from CIEHS, University of Louisville. First, let's think about why experimental design. Think about in a study, how many subjects or animals do I need to detect the effect I'm interested in? If the sample size is too small, there will be not enough power to detect the effect. However, if the sample size is too large, it will be a waste of resources such as time, money, and animals. Both situations are not what we want. So that's why sample size calculation is important. We need to calculate the minimal sample size to detect the estimated effect at experimental design phase. There are three key elements in sample size calculation: the effect size D, the significance level alpha, and the statistical power 1 minus beta. With these three elements, we can calculate our sample size. One most used effect size is Cohen's d, which is the difference between the mean of two population groups divided by the standard deviation of both groups. The unit of Cohen's d is standard deviation SD. And we normally set Cohen's d with 3 levels. The small Cohen's d will be with a value of 0.2, while the medium Cohen's d will be 0.5, and a large one will be with a value of 0.8 or higher. So how to estimate the effect size? One way is to calculate with means variation obtained from preliminary data or past similar studies. However, there are situations where there's no prior information. In this case, you need to make a suitable guess of the expected effect size based on your domain knowledge, so we can further calculate our sample size. Another two key elements in sample size calculation are statistical power and significance level. Before talk about these two concepts, we need to talk about two common types of statistical errors we want to avoid, which are type 1 error and type 2 error. Let's look at the table in the middle of this slide. The row here are the truths, which is the H0 null hypothesis, mu equal to mu0 being true, or the alternative hypothesis, HA mu equal to mu1 being true. And the decisions on the columns are do not reject H0 or reject H0. And the type 1 error is simply, while the truth being H0 being true, we actually make a decision of rejecting H0. And we normally set this probability to be alpha, which is corresponding to the small yellow area here on the right side. Notice here we denoted this as alpha divided by 2 because it's a two-sided test. And type 2 error is the situation where the truth is alternative hypothesis being true, but we make a decision of do not rejecting H0. We normally set this probability to be beta, which is corresponding to the right area here. And the statistical power is when the truth being alternative hypothesis being true, and we make a decision of rejecting H0. That is, we successfully reject a false null hypothesis. And this is corresponding to the big green area here on the right. You can see it's denoted as 1 minus beta, which is our power. And as our decision line here move from left to right, this yellow area, which is our type 1 error probability, will decrease. But our type 2 error probability, this red area here, will increase, which will also lead to our statistical power here, green area, decrease. So that's not what we want. In situation where we decrease our type 1 error, we need to pay attention that our statistical power will also decrease. Let's further talk about these two elements. The statistical power is the probability of rejecting the null hypothesis H0, while HA, alternative hypothesis, is correct. In other words, probability of detecting an effect which truly exists. We normally set this as 0.80, 80%. For intervention with minimal side effects, we may want to have a higher power in detecting effects. For example, a vitamin thought to have protective effects for heart attack, we may want to set the statistical power to be 90%. And significance level, which is also our type 1 error with probability alpha, is the probability that we wrongly reject the true null hypothesis. In other words, probability of claiming an effect which does not exist. This value, we normally set it as 0.05. So with these three elements we've talked about, we can calculate our sample size. And right now, we look at sample size calculation for different endpoints in experimental design. We divide our endpoints into three big categories: binary outcomes, continuous outcomes, and repeated measures. For binary outcomes and continuous outcomes, we want to consider one group sample and two independent samples. For binary outcomes with one group sample, let's consider when you have binary outcome, such as whether a certain event will happen or not, whether a certain disease will occur or not, and you want to conduct hypothesis test to say if the probability of the event occurs is different from a certain value. The hypothesis will be set as H0 p equal to P0 versus H1 p equal to P1. And we also set our significance level alpha and the power 1 minus beta. The D is the difference between P1 and P0, and it's also the difference in probability you want to detect. The effect size will simply be D divided by the square root of P0 times 1 minus P0. Then the required sample size is calculated using the equation below. Here, the Z alpha divided by 2 is the Z-score for our significance level, and the Z beta is the Z-score for our statistical power. Let's look at an example. Suppose one recent report suggested 26% of people without cardiovascular disease has elevated LDL cholesterol levels. And for patients with cardiovascular disease, the investigator assumes there will be a 5% difference in proportion of elevated LDL cholesterol. And we want to estimate the sample size to detect this 5% difference. We set alpha as 0.05 and the statistical power as 80%. Then we obtain the corresponding Z-score. After that, we inserted our numbers from this example into our equations in the previous slides, and we can obtain our sample size. We can also calculate the sample size using our code. The function will be pwr.p.test in the pwr package, and we need to insert the effect size, significance level, the statistical power, and the alternative, which is whether this test is a two-sided test or one-sided test. Let's move on to talk about binary endpoints with two independent samples. Consider when you have one binary endpoint and want to test whether the probabilities of this endpoint occurs in two independent groups are different. And we set the hypothesis as H0 P1 equal to P2 versus H1 P1 not equal to P2. And we set significance level alpha, power 1 minus beta. The pooled prevalence P will be P1 plus P2 divided by 2. and the effect size will be the difference between P1 and P2 divided by the square root of pod prevalence times 1 minus the pod prevalence. Assuming equal size for both groups, then the required sample size is calculated as below. The z-score here are the z-score for our significance level and our power. Also, let's look at one example. Approximately 40% subjects in intervention group and 30% in control group will develop a certain disease. And the prevalence, the pod prevalence will be calculated here. And we want to estimate the sample size to detect the difference between the intervention and control group. We set alpha equal to 0.05, beta equal to 0.20. That means our power is 80%. Then we can insert our values in our sample size calculation equation and obtain our sample size. We can also use the R code pwr.2p.test in the PWR package. With our effect size, significance level, power, and alternative, we are able to calculate the effect size. Oh no, calculate the sample size, sorry. Also look at the continuous endpoints with one group sample. Consider when you have a continuous endpoint and you want to conduct a hypothesis test to say whether the sample mean is different from a certain value. We set the hypothesis as null hypothesis H0 being mu equal to mu0 versus alternative hypothesis mu equal to mu1. And we set significance level alpha, power 1 minus beta. The standard deviation sigma, the D will be the difference between mu1 and mu0, and the effect size will be D divided by the standard deviation sigma. Then we can calculate the required sample size, which is using the below equation. Let's look at one example for this case. Suppose the mean glucose level for people free of diabetes is 95 milligrams per deciliter, with standard deviation 9.8. Hypothesize people who drink at least 2 cups of coffee a day has mean blood glucose level 100 milligrams per deciliter. And we want to estimate the sample size to test whether the fasting blood glucose is higher for people who drink at least 2 cups of coffee a day. So we set alpha to be 0.05, power to be 80%, and we calculate the sample size as below. The R code is using the function pwr.t.test in PWR package with our effect size, significance level, power. The type here will be whether the sample is one group sample or 2 group samples, and the alternative, 2-sided or 1-sided. And we look at continuous outcomes with 2 independent samples here. Consider when you have one continuous endpoint and want to conduct hypothesis test to say whether the means of these 2 independent groups are different. The hypothesis will be set as H0, mu1 equal to mu2, and H1, mu1 not equal to mu2. And we set significance level alpha, power 1 minus beta. D is just the difference between these 2 means. Sigma is the standard deviation of each group observations. The effect size will be D divided by sigma. Then the required sample size is calculated as below. Here is another example for this case. Estimate a sample size that's necessary to detect a 10 milligrams per liter difference in cholesterol level in diet intervention group versus control group. The standard deviation from similar study is 15 milligrams per liter. And we still use our alpha value of 0.05 and the statistical power 80%. And we obtain the corresponding z-scores, insert all these values into our equations and obtain our sample size. Our code will still be using pwr.t.test with effect size, significance level, power, but here the type will be set as to sample. Now let's look at the endpoints of repeated measures. Consider when you have an experimental design with two population groups involving multiple measurements of the same subject. For example, when you have a clinical longitudinal study with multiple visits for each patient, and you want to test A, the difference in the linear trends of two groups, or B, the time averaged difference of two groups. That's our two types of study goals you may have. And the rho, which is the ratio of the between subject variance divided by the within subject variance, and it's called intra-class correlation. No, the correlation is calculated by the between subject variance divided by the total variance, and the total variance is calculated by between subject variance plus within subject variance. And R is the number of repeated measurements here. TJ are our time points, which is same for all subjects, and the time variance is calculated here. The delta is our effect size. And we can get the equation for small n. And for different study goals, A and B, we calculate delta and adjust small n based on different study goal. For study goal A, which is to compare the slopes beta 1, beta 2 of different groups, the delta effect size will be calculated as the difference between the slopes divided by the standard deviation. Then the sample size will be adjusted this way. And for study goal, which is to compare time averaged difference, the effect size delta will be the difference between the group means divided by the standard deviation. Then our sample size will be calculated here. So for repeated measures, you can simply use the past software and use the module called Repeated Measure Analysis to calculate the sample size. BIFC do provide past software sample size calculation services. Now let's look at some extensions for sample size calculation. First, we look at the case where we have multiple groups instead of one or two groups. Suppose we have one endpoint with multiple groups, and we want to conduct k comparisons among the groups. Here, we need to use the Bufferoni correction to control our family-wise error rate. So what is family-wise error rate? It is the probability of making one or more type 1 errors among a family of tests or comparisons. So in this case, with multiple groups, we need to control our family-wise error rate by adjusting the significance level using alpha divided by k, where alpha is usually set as 0.05. Here, we need to be careful when conduct this multiplicity adjustment. The statistical power of each test will decrease as our adjusted significance level gets smaller. Another extension will be multiple primary endpoints, and we discuss 3 cases following the FDA recommendation. Case 1 will be one of the endpoints being significant indicates that the treatment is different from the control. In this case, we need to use multiplicity adjustments by applying Bufferoni correction with adjusted significance level alpha divided by k. K is the number of endpoints here. And for case 2, which is all endpoints need to be significant for a treatment to be effective, which is also called co-primary endpoints. In this case, no multiplicity adjustment is needed, but please keep in mind type 2 error may increase. That is, the power of the test could decrease in this case. And for case 3, we simply combine multiple primary endpoints into a single primary composite endpoint to avoid multiplicity issues. Let's also compare the animal study with clinical trials as for sample size calculation. We both need to consider practical constraints such as attrition, dropout, and we normally set the rates as 15%. For animal study, since it may often serve as pilot study, when there are no information for conducting sample size calculation, we could apply the resource equation method to decide the sample size, where the degree of freedom, which is total number of animals minus total numbers of groups, should lie within 10 to 20. And for clinical trials, we may have more ethical constraints we need to think about. So for sample size calculation, the regularly used software are PASS and R we've talked about before. So PASS is just a sample size calculation software with many different situations designed. And in BIFC, we have PASS softwares. So we can use PASS to calculate the sample size. And if we use R, we need to use the package PWR for power sample size calculation. These are the references we used for this slide. Thank you. And please contact us for experimental design and sample size calculation requests. And here are the email address for BIFC, for me, and also for Dr. Ma-Yin Kong. And Dr. Ma-Yin Kong's phone number and office number and my phone number, office number is also listed here. Thank you.